Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So in part number 4, we will discuss about steady flow application, where we will look at different type of devices in terms of how we want to implement the steady flow process for that device. Energy analysis of open system for steady flow device. So in terms of energy balance equation, all the steady flow device will use what we call the energy balance equation that we have learned before for the open system. So this is the general energy balance equation for the control volume system or for the open system. Okay, as we learned before, for the open system, when we consider the steady flow process, so the term for dE system over dt will be equal to 0 in the energy balance equation. So there are many examples in terms of open system where we need to implement the energy balance equation. For example, in thermodynamic 1, we will assume or we will consider this device as steady flow device. Okay, for example, in the schematic diagram, we have the cross-section drawing, simple cross-section drawing for the gas turbine engine. So in that engine, there are many components involved. For example, we have a diffuser. So this is the what I call simple schematic diagram that describe the diffuser. So we have mass in, mass flow rate in, and also mass flow rate out. We can see that in terms of what I call the cross-section area at the inlet, which is smaller compared to the cross-section area at the outlet of the diffuser. And then we have the second component for the gas turbine engine, which is referred as a compressor. Okay, for the compressor, we need to supply W in, rate of W in, and due to the open system, for the compressor, we will have mass flow rate in and also mass flow rate out. Okay, the third device or the third component for the gas turbine engine, we have a turbine. So in terms of schematic diagram, quite similar with the compressor, but for the turbine, we will have W out, rate of W out instead of W in. So for the turbine, we have W out, and we have mass in, mass flow rate in, and also mass flow rate out. So the difference in terms of shape between the turbine and also compressor. For the compressor, the volume start with higher volume to the lower volume due to the compression. However, for the turbine, start with lower volume to higher volume due to the expansion process in the turbine. Okay, next, the device involved in the gas turbine engine is the device or the component that we call nozzle. Okay, so the nozzle in terms of shape quite similar with the diffuser. The difference is I call the size of the cross-section area at the inlet bigger compared to the cross-section area at the outlet for the nozzle. So we have mass flow rate in and also mass flow rate out for the nozzle. Other type of system we will learn in terms of implementation of energy balance equation and also the steady flow process. So we have the heat exchanger. Okay, for the heat exchanger, for example, this is one type of cross-section what I call schematic diagram for the heat exchanger, where we have two different type of fluid A and also fluid B, where these two type of fluid will not mix in the heat exchanger. So for fluid, for example, here for fluid B, we have one inlet where we have m dot in B, and also one outlet m dot out B. However, for fluid A, also we will have one inlet and so one outlet, but now for different fluid. So we have another m dot in A and also m dot out A, and both fluid are not mixed. And also we have another device that normally use the what called steady flow process that we call a mixing chamber. Okay, so if you look the difference between a mixing chamber and also a heat exchanger, So the mixing chamber, actually the fluid, the different type of fluid will mix in the main body of the mixing chamber. Okay, for example, here the mixing chamber consists of 2 inlet and also 1 outlet, where we have fluid A mixed with fluid B. So fluid A, at the inlet of the fluid A, we have m dot in A. At the inlet for the fluid B, we will have m dot in B. So at the end, after mixing process, at the outlet, so we'll have m out dot equal to m in dot A plus m in dot B, by referring to the principle of conservation of mass. Okay, so there are many other types of device that we learn. For example, we also have the what I call the system involved with pipe, duct, and also the valve, throttling device, and so on. Okay, so all the device that we will discuss in thermodynamic 1, for example, for the open system, we will use this energy balance equation, the mass balance equation, and also the concept of steady flow process. The first device that we will discuss in this part are the nozzle and also the diffuser. So we discuss in terms of the characteristic of the device, and at the end we will get the final energy balance equation for the device. Nozzle and diffuser. So the application of the nozzle and also the diffuser can be found in jet engine, rocket, spacecraft, and also the garden hose. The photo shows an aircraft. So at the back of the aircraft, you can see that the aircraft engine, actually the engine is a gas turbine engine. So in terms of operation, so the air will enter the engine first through the component that we call a diffuser. Okay, and the air will enter the diffuser and then come out from the diffuser to enter the compressor. Okay, so this is the what I call the simple schematic diagram for the diffuser, where we have mass flow rate in and also mass flow rate out, where we can see clearly the diameter of the cross section area at the inlet is smaller compared to the cross section area at the outlet of the diffuser. Okay, next, the air, the compressed air from the compressor will enter the what I call the compressor chamber and then enter the turbine. So the exhaust gas from the turbine will enter the final component here, as shown in this schematic diagram, that we call a nozzle, and then the exhaust gas will come out from the engine through the outlet of the nozzle. So this is the cross section, the simple cross section drawing for the nozzle. Okay, so the function of the nozzle to produce the thrust force of the engine. Okay, so if you compare in terms of the difference between the diffuser and also the nozzle in terms of cross section area at the inlet actually bigger compared to the diffuser. So for the nozzle at the inlet, in terms of cross section area, will have bigger size compared to the cross section area at the outlet of the nozzle. So for the nozzle also we will have a mass in, mass flow rate in, and also mass flow rate out. So that is the difference between the diffuser and also the nozzle. Okay, steady flow engineering device for nozzle and also for the diffuser. So in this part or in this slide, we discuss more detail about the nozzle and also the diffuser in terms of characteristics and also the energy balance equation that involve. Okay, for the diffuser, in terms of function, the diffuser will increase the pressure of a fluid by slowing it down. So this is the schematic diagram for the diffuser, where we have called mass flow rate in and also velocity at the inlet V1 bar, and also at the outlet we have m dot out, mass flow rate at the outlet, and also the velocity, average velocity of the fluid at the outlet, V2 bar. Okay, so if you look to this schematic diagram, in terms of cross-section area at the inlet for the diffuser is smaller compared to the cross-section area at the outlet of the diffuser. Okay, so based on the what I call the function of the diffuser, we will have in terms of pressure, the pressure at the outlet will be higher compared to the pressure at the inlet of the diffuser, and the velocity of the fluid at the outlet of the diffuser, V2 bar, is far lower compared to the velocity of the fluid at the inlet of the diffuser, V1 bar. However, for the nozzle, in terms of function, the nozzle will increase the velocity of the fluid at the expense pressure. Okay, so now we have the second schematic diagram that represent the nozzle schematic diagram. So in terms of shape, if you compare to the diffuser, the nozzle shape will be reversed if compared to the shape of the diffuser. Okay, so for the nozzle, the cross-section area at the inlet will be greater compared to this cross-section area at the outlet of the nozzle. So at the inlet we have mass flow rate m dot in with fluid velocity v1 bar, and at the outlet we have mass flow rate m dot out with fluid velocity at the outlet v2 bar. So in terms of criteria, so in terms of pressure, P2 for the nozzle at the outlet is lower compared to the pressure at the inlet of the nozzle. However, in terms of velocity at the outlet for the nozzle V2 bar far greater compared to the average velocity at the inlet of the nozzle V1 bar. The other characteristic for the nozzle and also diffuser in terms of energy, so in terms of rate of heat transfer, Q dot, so the value of Q dot for the diffuser and also nozzle is very small due to the high velocity of the fluid involved in the diffuser and also the nozzle, because that we considered due to the high velocity there is not enough time for the heat transfer process occur in the diffuser and also in the nozzle. So Q dot, rate of heat transfer in the diffuser and also in the nozzle, we consider more or less equal to 0. So no rate of heat transfer or heat transfer process in the diffuser and also in the nozzle. Okay, next about the rate of work involved, W dot. So in the diffuser and also in the nozzle there is typically no work involved, because in the diffuser and also nozzle there is no movement of the mechanical works, shaft, what I call the moving boundary and so on in the diffuser and nozzle. So that's why typically no work involved in the diffuser and also in the nozzle. So the term for W dot, rate of work or work, will be equal to 0 for the diffuser and also for the nozzle. Okay, next about the potential energy that involved. So PE, in terms of change of potential energy in the diffuser and also in the nozzle, the change is negligible. Okay, so normally I call the point that we refer based on the inlet and also the outlet, the level is the location of the point of the inlet and also outlet is at the same level. Okay, at the same level. So we can consider that no delta PE, which is delta PE equal to 0. However, for the kinetic energy KE, the change cannot be neglected for the diffuser and also for the nozzle, because the process involves very high velocity of fluid. So the change of kinetic energy cannot be neglected for the diffuser and also the nozzle. So we need to count the value of kinetic energy change in our analysis for the diffuser and also for the nozzle. Okay, now we look to the energy balance equation for the nozzle and also for the diffuser for the open system, which is open system and also involve steady flow process. So this is what I call the general energy balance equation. Okay, so we want to know what is the energy balance equation specific for the nozzle and also for the diffuser. Okay, due to the no heat transfer process, rate of heat transfer Q dot. So in the equation will be no Q in dot and also no Q out dot. Diffuser and also nozzle not involve any work. So in the equation will be no W in dot and also no W out dot. So the remaining term is just the term for the E mass in and also E mass out. So in the equation for E mass in, E mass out, involved is enthalpy, the summation of enthalpy, summation of kinetic energy, and also summation of the potential energy terms. So because the potential energy term in terms of change is 0, so Gz for the inlet and also Gz for the outlet will be 0. We can neglect the value. So the remaining term for the energy balance equation will be total in m dot multiplied by h plus v bar square divided by 2 equal to summation or total out m dot multiplied by h plus v bar square divided by 2. So this is the general energy balance equation after we cancel out whatever terms that not involved for the diffuser and also for the nozzle. Okay, so because the diffuser and also the nozzle only will have one outlet and one inlet, so we have this final equation for the diffuser and also for the nozzle, where number 1 stands for the inlet condition, number 2 stands for the outlet condition for the device. So we have m.1 multiplied by h1 plus v1 bar square divided by 2 equal to m.2 multiplied by h2 plus v bar 2 square divided by 2. So this is the final energy balance equation for steady flow process for the diffuser and also for the nozzle. Example 4.5. So this example will involve with a diffuser. Air at 10 degrees Celsius and 80 kilopascal enters the diffuser of a jet engine steadily with a velocity of 200 meter per second. The inlet area of the diffuser is 0.4 meter square. The air leaves the diffuser with a velocity that is very small compared with the inlet velocity. Determine A, the mass flow rate of the air, and B, the temperature of the air leaving the diffuser. Okay, first, what we need to do, just draw the simple schematic diagram and put whatever data given in the equation on the diagram. Okay, so this is the diagram for the diffuser. We have inlet and also outlet. Okay, the boundary. So the substance that enter the diffuser is an air. And we can treat the air as an ideal gas. So the condition at the inlet, we have T1 equal to 10 degrees Celsius, P1 80 kilopascal, average velocity V1 bar equal to 200 meter per second, and the cross-section area at the inlet A1 equal to 0.4 meter square. However, at the outlet, because in the question mentioned that the velocity that is very small, and also we have learned that the velocity, the outlet of the diffuser is far lower compared to the inlet velocity. So V2 bar more or less equal to 0. We can ignore the value of V2 bar. And the process involved the steady flow process. So E system dt will be equal to 0. Okay, so first we answer the question A, where we need to determine the mass flow rate. So now, in order to determine the mass flow rate of air, so we need to know what is the suitable equation that can be used. So the equation that suitable to use is this equation, where m1 dot equal to rho, density of the air, multiplied by A, the cross-section area, multiplied by velocity, the average velocity V bar. And we can change the equation. So the equation also equal to 1 over specific volume multiplied by A multiplied by V bar. Okay, so based on this final equation for the mass flow rate m1 dot, so we already have the value for A1 and also the value of V1 bar. So the remaining term that we don't have the value is the specific volume V1. So now what we need to find the value of V1 before we get the answer for V1 bar. So we can use the what I call the ideal gas equation, PVMRT. So rearrange the equation. So V1 specific volume at the inlet equal to R gas constant multiplied by T1. So make sure if when we use the ideal gas of air equation, so the temperature T1 must be in Kelvin divided by P1. So gas constant normally given, where the value of gas constant equal to 0.287 kilopascal meter cubic per kg Kelvin multiplied by T1. T1 equal to 10 plus 273 Kelvin divided by 80 kilopascal. So we'll get V1 equal to 1.015 meter cubic per kg. So substitute all the value into the equation of M1 dot. So we'll get M1 dot mass flow rate of the air will be equal to 78.8 kilogram per second. Okay, for question B, we need to determine the temperature at the outlet of the diffuser, T2. So first, we analyze the energy balance equation for the diffuser based on the characteristic that we have learned before, and also the information that given in the question. So based on the characteristic of the diffuser, will be no heat transfer, no work transfer, and also no potential energy change in the system, okay, in the diffuser. And we have additional information in the question where the value of V2 is very small, so the term of kinetic energy for the outlet condition will be neglected. However, the kinetic energy terms at the inlet we need to consider. Okay, so this is the what I call the simplified equation, energy balance equation for the diffuser. So just rearrange the equation because the value of M1 dot and also M2 dot is equal due to the conservation of mass principle, because for the diffuser we only have one inlet and also one outlet, so the mass flow rate will be equal. Okay, so we have the final equation where we have H2 equal to H1 plus V1 bar square divided by 2. So from this equation we can get what I call information for state number 2, or the condition at the outlet of the diffuser. So at least we need to have one data for the outlet condition in order to obtain the outlet or the exit temperature of the nozzle. Okay, from this equation we need to determine the value of H1, because the value of V1 bar already given in the equation, which is 200 meter per second. So now the term that we don't have is H1 enthalpy. So because the substance is ideal gas, so we can use the ideal gas of air table at the inlet. Okay, so from ideal gas of air table, so we have information in terms of enthalpy and also in terms of temperature. So we can get from the table, we can get the value of H1, but we need to make interpolation. So we need to make interpolation between the temperature and also the enthalpy. So because we know the temperature is 10 degrees Celsius plus 273, so we'll get the temperature is 283 Kelvin. So H1 equal to enthalpy at 283 Kelvin, and the value is equal to 283.14 kilojoule per kg. So the value we obtain through the interpolation. And at the outlet, we can get the value of H2 based on the equation that we have, that we derive from the energy balance equation. Okay, but remember the term for kinetic energy in joule per kg and the value of H1 in kilojoule. So you need to make sure that you use the same unit when you make calculation. So for this case, I change the unit for H1 from kilojoule per kg to joule per kg. Okay, and then we calculate, we will get H2 equal to 303.14 kilojoule per kilogram. Okay, based on the value of H2 enthalpy at the exit, so we can manipulate this value by using the ideal gas of air table. So we can from the value of H2 we can interpolate make interpolation between enthalpy and also temperature value in the ideal gas of air table to obtain the temperature at the outlet of the diffuser. So make interpolation, so we'll get the value of temperature of air, the temperature of air at the outlet of the diffuser equal to T2 equal to 303 Kelvin. Example 4.6, the example for the nozzle, for a nozzle. Steam at 1.8 megapascal and 400 degrees Celsius steadily enters a nozzle whose inlet area is 0.02 meters square. The mass flow rate of steam through the nozzle is 5 kg per second. Steam leaves the nozzle at 1.4 megapascal with velocity of 275 meter per second. Heat losses from the nozzle per unit mass of the steam are estimated to be 2.8 kJ per kg. Determine A, the inlet velocity, and B, the exit temperature of the steam. Okay, so now the substance is different compared to the previous example. So now the substance is water or steam. Okay, A, we need to determine the inlet velocity. First, draw the schematic diagram and put whatever data given in the equation on the diagram. Okay, so we have the diagram for the nozzle. So we have inlet and also outlet. And the substance inside the nozzle is steam. T1 equal to 400 degrees Celsius, P1 1.8 megapascal, M1 dot mass flow rate equal to 5 kg per second, A1 cross-section area at the inlet is equal to 0.02 meters square. The condition at the outlet of the nozzle are P2 equal to 1.4 megapascal, V2 bar, the average velocity at the outlet equal to 275 meter per second. And we have, for this case, we have heat losses to surrounding. So part of the heat transfer in the energy balance equation we need to consider equal to Q equal to 2.8 kJ per kg. Okay, now the equation that can be used to determine the inlet velocity is the formula for mass flow rate, M1 dot equal to rho AV bar equal to 1 over specific volume V1 multiplied by A V1 bar. So in terms of data that we already have the value for M1 dot, which is equal to 5 kg per second, and also we'll have the value for A, which is equal to 0.02 meter square. So the remaining terms that we need to know before we calculate the value of V1 bar, what I call the inlet velocity, is the what I call the parameter for specific volume V1. Okay, so we need to determine the value of V1 first before we calculate the value of inlet velocity. So at the inlet, because now involved with water, so we need to determine the phase of the water condition at the inlet and also at the outlet. So at the inlet, the pressure given is P1 equal to 1.8 megapascal and T1 equal to 400 degrees Celsius. So what we need to do, we need to check by using saturated water table. We want to check the phase. Okay, based on the saturated water table, find out the what I call the saturated temperature at 1.8 megapascal. So we need to make interpolation. So T saturated at 1.8 megapascal equal to 207.76 degrees Celsius. So we get the value through interpolation, and then compare this T saturated with the temperature given T1. So T1 is greater than T saturated at 1.8 megapascal. So confirm the phase is superheated. Okay, now we already know that the phase is superheated. So based on the data given, P1 equal to 1.8 megapascal and also T1 equal to 400 degrees Celsius. So we need to refer to the superheated vapor table. Okay. So the pressure is 1.8 megapascal. The temperature is 400. So from this table, we can determine the value of specific volume V, where the value in the table of P 1.8 megapascal will give you the value of V1 for the inlet condition, specific volume at the inlet condition, which is equal to 0.16847 meter cubic per kg. Okay, so also try to determine the value of enthalpy H1 because later on you may need to use this value. So from this table directly we can obtain H1 equal to 3250.9 kJ per kg. Okay, so by using the equation for mass flow rate, M1 dot equal to 1 over V1 multiplied by A1 multiplied by velocity, average velocity at the inlet. Just substitute the value, so we'll get the steam velocity at the inlet V1 bar equal to 42.1 meter per second. Okay, next we want to answer the question. So the question asks you to determine the temperature of the steam at the exit of the nozzle. So we will implement the steady flow process where dE system over dt equal to 0. So we need to analyze the energy balance equation for the nozzle based on the characteristic and also the data given in the question. Okay, so for this case, for the nozzle case in this equation, we will have no Q in, no heat gain, but we have Q out, Q loss, because the equation mentioned about the Q losses to surrounding. We don't have any work in, work out. We don't have we neglect the effect of the potential energy change, and the remaining term will be this equation where we have M1 dot multiplied by H1 plus V1 bar square divided by 2 equal to M dot 2 multiplied by H2 plus V2 bar square divided by 2 plus the heat loss to surrounding Q out dot. Okay, so divide the equation with mass flow rate, because mass flow rate already given, and we know that based on the mass conservation of mass principle, so M1 dot equal to M2 dot. Okay, divide all the terms inside the equation with mass flow rate. Okay, mass flow rate already given, and we know that the value is the same, so we can eliminate the term for M1 dot and also M2 dot in the equation. So the final equation for this one, for the energy for the nozzle, will be H1 plus V1 bar square divided by 2 equal to H2 plus V2 bar square divided by 2 plus Q out. The aim actually, we want to get one data that involves the outlet of the nozzle in order to determine the temperature at the exit of the nozzle. So from this equation, we can our aim, we want to determine the value of enthalpy H2. So from the value of H2, we can determine the temperature of T2. Okay, so rearrange the equation. So we substitute all the value that we have for V2 bar, V1 bar, Q out, and also H1. Okay, so H1 we already determined before this. So make sure that all the terms into the equation of H2, we use joule per kilogram unit. Okay, because we want to have what we call consistency in terms of unit in our calculation. Okay, so we'll have at the end, we will have H2 equal to 3211.9 kJ per kg. Okay, now at the outlet, in terms of data, what we have, so we have P2 equal to 1.4 megapascal and also H2 equal to 3211.9 kJ per kg. So we already have two data. For water, it's enough to determine the phase. So first we need to determine the phase. Use saturated water table. Okay, so at 1.4 at 1.4 megapascal, because we have here we have the value of H, so we need to make comparison between the value of H given with the value of HF or Hg in the saturated water table at 1.4 megapascal. Okay, so if you look at the value of Hg at 1.4 megapascal equal to 2.790.0 kJ per kg. So now compare with the what I call H2 value that we obtained. So H2 greater than Hg at 1.4 megapascal. So confirm the phase is superheated. So now we need to refer to the superheated water table. Sorry, superheated vapor or superheated water table in order to obtain the temperature of T2. Okay, based on the data that we have, P2 equal 1.4 megapascal, H2 equal 3211.9 kJ per kg, and we know that the phase is superheated, so we use the superheated vapor table. Find out the table for pressure equal to 1.4 megapascal. Okay, so in order to obtain the temperature, so we need to make interpolation between the enthalpy and also the temperature. Okay, based on the value of H2 3211.9. Okay, so the temperature that we obtain through the interpolation for the temperature at the exit of the nozzle is T2 equal to 378.6 degrees Celsius. Okay, that's how we answer the question involved is nozzle and the substance involved is water.